Welcome to this MOOCs online video course Theory of Yarn Structure. Today we are going to start module 4 Helical model of fibers in yarns. As you are aware of, helical model of fibers in yarns is a very popular model and often quoted in research articles. It is a relatively old concept in theory of yarn structure. Started from Cochrane 1828, then Muller, then Marchik, Gegoff, Schwarz, Brasler, Budnikov, Neskers, Treller. Many scientists worked on helical model of fibers in yarns. Today this model is well established. The importance of helical model of fibers in yarn lies in three distinct cases. This model helps us to calculate number of fibers present in cross section of yarn. This is a very big importance of this model. Second, another very important application of this model is it explains yarn retraction. What is yarn retraction? When you twist a yarn, the length of the yarn shortened. This phenomenon is called yarn retraction. In some books you will find out yarn contraction. They basically denote the same phenomenon. However, little difference exists between them. Why it was important to understand yarn retraction? Because what governs yarn retraction? If we do not know about this, we will not be able to control the shortening of yarn. So, it was necessary to understand the phenomenon of yarn retraction. This model, helical model of fibers in yarn, explains yarn retraction phenomenon scientifically. Third important application of this model lies in yarn twisting. What happens if we go on increasing the twist in yarn? After the so called saturated twist, if we still increase the twist, then the coils do not go inside the yarn and we obtain a very undesired structure of yarn. So, we should not go to that level of twisting. That means, in practically also there is a limit of twisting. What is that limit of twisting? We must know beforehand. We should not reach to that twist, then we will spoil yarn structure. So, basically these three phenomena are well explained by helical model of fibers in yarns. In this module, we will study these three phenomena under helical model of fibers in yarns. So, first let us clarify this concept, what is helical model of fibers in yarn. The helical model of fibers in yarn is based on 4 important assumptions. First 3 are very general assumptions, and the fourth one, very important, is a very special assumption. The first assumption, fibers follow helical path in yarn. So, you see it is a yarn, cylindrical yarn, and this fiber follows helical path. Here you see thick portion of the fiber which comes to on the surface, then the fiber goes inside dotted line, you do not see them, then again it goes to surface. So, you see them thick black line. So, the fibers follow helical path . Second, all the helices have a common axis of rotation, that is yarn axis. Okay. Third, all coils, it seems to be a coil. So, all coils have same height. So, little elaborate the first assumption, fibers follow helical path with same sense of rotation. Let us write in this manner. So, as I told you, helical model is based on 4 assumptions. The first 3 are very general assumptions. First assumption, fibers follow helical path inside the yarn structure with a same sense of rotation. So, the direction of rotation is same. Second, all helices have a common axis, that is your yarn axis. Third, all helices have a common height. Coil height is same. Fourth, the very special assumption, packing density is same at all places inside yarn. Packing density is same at all places inside yarn. So, actually the first 3 are quite general assumption, but the fourth one is a very special assumption. Why? In practice, you know, mu packing density is not constant. However, it is a function of r. So, this is the practically we see this kind of behavior. the real behavior. This probably goes a little low, something like that. But here the assumption is same, that means what we think is that you probably think in this manner. So, this is the difference, right. So, the red is indicating the real behavior, however, the blue indicates this assumption. Now, this helical model is based on these 4 assumptions. Right. Now, this image you see, it is basically a yarn cylinder. It has a diameter capital D, and inside this cylinder of diameter D there is one small cylinder of radius r, where a fiber helix is shown. This helix makes an angle beta from yarn axis. If you unroll this cylinder, make it flatten, then you will obtain this triangle, where the base of the triangle is equal to 2 times pi times small r. R is yarn radius, D is yarn diameter. And this beta is the twist angle. The height of this triangle is 1 by z. Z is number of turns per unit length of the yarn. So, this length is 1 by z and this angle is beta. So, what we obtain is tangent beta is 2 pi r z, right. We obtain this one, tangent beta is 2 pi r z. So, this is the concept of helical model. Now, we will find out number of fibers present in yarn cross section. So, our aim is to determine a relation which will predict number of fibers in yarn cross section. You will ask me, what is the need to predict? We know that n is this. This is true. This is true. Capital T is very easy to find out, small t is also very easy to find out, but k n, coefficient k n is relatively difficult to determine experimentally. Why? Because you require microtome apparatus, you require suitable utensils for cutting cross sections of yarn, you require a light microscope. So, many common textile laboratories may not have these facilities. That is why it becomes very difficult to find out number of fibers experimentally, but often we need to predict it for theoretical research or for some empirical research. We need to find out what is the value of n. How we find out? That is why it is necessary to find out a relation, theoretical relation, that predicts number of fibers in yarn cross section, right. So, our aim is to find out a relation that predicts number of fibers in yarn cross section, and we will use helical model for that purpose. What do we see here in this image? This is the cross section of the yarn, lot of fibers are present, say n number of fibers are present. This is yarn diameter, and we see one thick annular ring which is situated at a distance r from yarn center, and the thickness of this annular ring is d times r, right. That means, first we will find out how many fibers are present in this annular ring. Then if we integrate that expression from r is equal to 0 to r is equal to d by 2, we will find out number of fibers in yarn cross section, right. So, let us follow the same strategy. Now, what is the area of this ring? Two pi r dr. So, this is the area of ring. What is the area of fibers in the ring? This is the area of the ring. What is the area of fibers in the ring? If we multiply this by packing density, we will find out, because packing density, one of the interpretation is area of fibers divided by area of yarn, right. So, 2 pi r mu dr. Mu is packing density, which is constant at all places. Packing density here is mu, here is mu, here is mu, everywhere packing density is same. That was our fourth assumption of helical model. Right. Let us think that this area is equal to this. You remember the symbol capital S? Substance cross sectional area of yarn, which basically consists of sectional areas of fibers. So, ds. Okay. Right. Now, we will continue with this image with one more additional image. Here it is shown. So, what we found, ds is 2 pi r mu dr. This image is basically the image of a fiber, inclined fiber. Because of the twist, fiber is not straight, they are not parallel along yarn axis, they are inclined at an angle. This angle is beta. So, this area is the sectional area S star, and if we go along this axis at cross section, we will find out cross sectional area. This is your this S, Okay. Now, what is the relation between these two areas? This we have already found out in module 2. S star is equal to S by cos beta. Okay. Now, you tell me how many fibers or fiber sections precisely are present in this annular ring. They are very small in number. How many fibers or how many fiber sections are present in this small ring? How will you find out? Suppose that number is dn, total area divided by mean section area, is not it? So, total area is your 2 pi r mu dr divided by section area S star, is not it? So, if we substitute dr, if we substitute S star, then we find out this expression, right. So, what was our target? Our target was to find out an expression for n. How will you find out n? If you integrate, you will find out n. So, let us integrate. R is equal to 0 d by 2 pi by S mu r cos beta dr. Now, beta is a function of r, is not it? How they are related? Okay. Before going to that, this 2 pi is constant, small s is fiber cross section area, also constant, mu we assumed constant because of fourth assumption. So, then r is a variable and beta is also a function of r. So, what we will do now, n is equal to integration r is equal to 0, r is equal to d by 2 pi by S mu r cos beta. Let us write cos beta as 1 by sec beta dr. Zero d by 2. Now, basically what we want to convert this as a function of r. What is sec beta? Square root of 1 plus tan square beta dr. What is tan beta? We have already derived it. Dr. Now, we will be able to write it in a better manner. 2 pi by s into mu, this we assume to be a constant integration r dr square. This integration we have to solve. We will follow method of substitution for this. So, what we will consider 1 plus 2 pi r z square is equal to, we will consider x square. Okay. So, right. So, r dr is equal to 1 by 4 pi square z square into x dx. This substitution we will consider. Okay. So, then what we will write, n is equal to 2 pi by s into mu. This limit now we will change. When r is equal to, if we r is equal to 0, then what will be x? X equal to 1. When r is equal to d by 2, when r is equal to d by 2. So, this 2 will cancel, pi dz, x will be root over 1 plus pi dz square. Okay, clear about this limits. So, now we substitute. So, x will be 1 and this will be 1 plus pi dz square, upper limit, and r dr. So, if it is r dr, so then we will write x dx by 4 pi square z square, and in the denominator also, in the denominator was x. So, we write x. So, then it becomes simple, 2 pi by s mu integration 1 to 1 plus pi dz square 1 by 4 pi square z square dx. So, this 4 pi square z square is also constant, it can come out of this integration. So, 2 pi mu s 4 pi square z square 1 plus pi dz square into dx. Integration of dx is equal to x. 2 pi mu s 4 pi square z square integration x, lower limit 1, upper limit 1 plus pi dz square. Right. Now, let us make it little simple. So, now what we see here is that this 2 and this 2, this pi and this pi square pi. So, what we do, n is equal to, let us write it here as pi d z square. If we write in the denominator pi d z square, then what will be in the numerator? In the numerator it will be mu pi d square, right, because 1 pi was already there. So, pi square d square z square pi z square, all right, and then you will have this 2 times s. Okay. Now, n is equal to this. In the numerator, what we will do? We will write 2 into pi d square by 4 into mu into 1 by s. Root over 1 plus pi d z square minus 1, right, pi d square by 2 s into mu. Clear? Now, what is pi d square by 4 into mu? That is equal to capital S. So, we can write 2 into capital S by small s pi d z square root over 1 plus pi d z square minus 1. Okay. What is capital S? Substance cross sectional area of yarn. What is small s? Cross sectional area of a fiber. So, this ratio capital S by small s we have already derived that this is equal to capital T by small t, right. So, that is equal to relative fineness tau. You remember in module 2 this relationship we have already derived in module 2. Relative yarn fineness tau is equal to capital T by small t, yarn count in tex by fiber fineness, that is equal to substance cross sectional area capital S divided by fiber cross sectional area small s. So, we can now write down 2 into tau pi d z square root over 1 plus pi d z square minus 1. This relationship is what we were looking for. So, we have now got a relation for n tau relative fineness capital T by small t, very easy to determine practically. Pi d z also possible to determine because z is already known to you, or using module 3 we will be able to determine z and capital D also root over 40 by pi mu rho. So, we will be able to determine capital D. So, n is now possible to calculate using this expression, right. Okay. Let us now proceed a little further. This is your n, and what we know, n is k n into tau. This is true always, whether it is helical model or not does not matter. This expression is true always. Then what is your k n? K n is n by tau. These expressions we have already derived in module 2, n by tau. So, if we substitute n from here, what we see is 2 by pi dz square root over 1 plus pi dz square minus 1, right. So, we can also find out the value of k n. We can calculate the value of k n, also we can find out the value of small n, number of fibers in yarn cross section. Now, this is also another important expression. So, let us put a star mark here. Okay. It is also possible to express n and coefficient k n in a different manner. So, let us do that. What is your kappa pi dz and what is your pi dz tangent of beta d? Beta d surface fiber twist angle. Okay. Then if we substitute here, first let us find out for k n. K n is 2 by pi dz square tan square beta d within square bracket root over 1 plus pi dz square. So, pi dz square is tan square beta d minus 1, right. Look at the expression within square bracket, root over 1 plus tan square beta sec square beta, square root of that sec beta. So, 2 tan square beta d sec beta d minus 1. What is sec beta d? 1 by cos beta d. So, 2 and tan square beta d is sin square beta d by cos square beta d. So, 2 cos square beta d by sin square beta d 1 minus cos beta d by cos beta d, right. Further 2 cos beta d 1 minus cos beta d by sin square beta d. Sin square beta d is 1 minus cos square beta d. Further we can write 2 cos beta d 1 minus cos beta d 1 plus cos beta d 1 minus cos beta d. Now, what we see is that here these two terms are cancelling out. So, what we obtain, K n is equal to 2 cos beta d divided by 1 plus cos beta d, is not it? Simple expression. Hence, it is more acceptable. So, we found quite simple expression for coefficient k n, 2 times cos beta d by 1 plus cos beta d. It can be made further simple, you can try for that. Now, what we see that if we know kappa pi dz, if we know diameter, pi mu rho, for that you need to know mu. So, this mu and this z, this we can know from module 3, right. So, by using those two expressions of module 3, we can find out mu and z. Remember those two expressions. So, by using these two expressions, we can find out mu and z. How? First we will find out this value, then corresponding mu value we will find out. This mu value we will substitute here, then corresponding z value we will find out. So, theoretically we will be able to determine mu and z, then we will be able to determine d, then we will be able to determine pi dz kappa. So, if we know that is equal to your tangent of beta d. So, we will be able to determine beta d. If we know beta d, we will be able to find out k n. So, by using this what we described just now, we will be able to determine the value of coefficient k n, and if we know coefficient k n, then we will be able to find out n, because coefficient k n is known, capital T by small t are very well known quantities for yarn. We will be able to find out this small n, number of fibers present in yarn cross section, right. So, now we will go and talk about this behavior of this expression. What expression? K n is equal to 2 times cos beta d by 1 plus cos beta d. So, this expression is graphically plotted here. Along the x axis, beta d in degree is plotted, then we calculated k n from here and we plotted k n along this y axis, and this is the curve of k n for different value of beta, right. Generally this angle beta d for common yarn will lie from say 20 degree to 30 degree. So, for common yarns this angle beta d lies from 20 degree to 30 degree. When beta d is 20 degree, beta d is 20 degree here, corresponding Kn is 0.97, is not it? Corresponding Kn is 0.97, and when beta d is 30 degree, corresponding Kn will be close to 0.93. So, equal to Kn 0.97. So, for ring spun yarn this Kn lies from 0.93 to 0.97. What is the average? Average is 0.95. So, average is somewhere here 0.95, that means somewhere here, right. So, that is why you remember in module 2 when we define coefficient Kn, that time we told for ring yarn Kn is typically 0.95 and for rotor yarn Kn is typically 0.80. That 0.95 is basically coming from here. But in practice the value of Kn is little higher for DN yarn. Than that predicted by the model. Little higher, that is what we observe. Why is it so? Probably our fourth assumption, packing density is same at all places in yarn, is the reason for this behavior. However, packing density is a function of R, and what is that function is still unknown. So, unless and until we characterize this function properly and put it mathematically inside the integration and solve for that, this can be done, possibility exists, but before that we have to solve for that function, right. In any way, so we have demonstrated you how this helical model can be used to find out the number of fibers present in yarn cross section, as well as how to determine coefficient Kn in a yarn. So, as I told you, this has been a very important contribution from helical model of fibers in yarn. Another important contribution of helical model of fibers in yarn lies in explaining the phenomenon of yarn retraction. When you insert twist, the length of yarn shortened. This behavior is known as yarn retraction. What is the fundamental principles lying behind yarn or underlying yarn retraction can be understood from helical model. This we will talk in the next class. Thank you for your attention.